All right, this is the second half of the lecture for day 3, and in this video we're going to be talking about some actual statistics, and we're going to be focusing on quantitative variables. Namely, we're going to be talking about different ways of graphing them, so our focuses are going to be for histograms and box plots, but we're also going to be talking about ways of describing data, so describing a particular distribution by talking about its shape, its center, and its spread. Okay, so first talking about graphs. Okay, so here we have a histogram. Hopefully everyone's familiar with how these work, but just to quickly go over that, if, say, we had a data set that was a collection of people's ages, so here we have all the ages of people who were aboard the Titanic, what we do is we break the ages up into regions or bins. So for example, we have the 0 to 5 bin, the 5 to 10 bin, etc. And then we count how many people are in that bin, and we plot on the y-axis the count or the number that fall into that category. So one nice thing about histograms is that they let us look at it and get a really good sense of what the distribution looks like. And we'll be talking more in a minute about ways that we can in words describe the shape, spread, and center of these histograms. Okay, another example that we're not going to talk a ton about is the dot plot. The dot plot is extremely similar to a histogram. The main difference is that, well, we have dots rather than just heights, and a main advantage is that you can sort of see individuals as separate dots. So it gives you a little bit more sense of what's going on there. That said, histograms are definitely more common. Okay, we also have the stem and leaf plots. Now these ones are probably even less common, but they do show up every now and then, so it's worth mentioning them. So a data set that might go into something that looks like this would be, let's say that our Class A data set is 60, 68, 70, 75, etc. Right. And so the way that you would build out the stem and leaf plot would be you would take everything but the last digit and you would put it in the middle, and then you would record the last digit sort of as another increment in a dot plot or in a histogram. So there's a 60 because, well, we have a 6 in the stem and a 0 in the leaf. And then we have 68, and then we have 70, etc. So this is sort of a hybrid of a histogram together with the actual data. So there's advantages to it, namely that you can look at it and get a visual impression of what these distributions look like, while also being able to see the actual data points. So this certainly has its uses, though it's definitely less common than histograms and box plots. Okay, last up are box plots. And this is one that you likely have seen before, but you may not have actually worked with before. So box plots use medians and interquartile range, which we'll talk about later in this video, to give a sense of where exactly the distribution is. And these are very useful when doing something like comparing a bunch of different distributions all at once. So here we have the average wind speeds at different months of the year, and for each month we're going to calculate all of the wind speeds. So the data set here would look like, all right, the January we're going to have probably, let's say, 31 numbers, and we're going to calculate the median, the interquartile range, which again we'll talk about in a minute, and the min and the max. And together this is going to let us build out this box plot. Cool. Okay, so those are the methods of displaying data that we're going to talk about. Next up is how we can actually describe these distributions. And we're going to start off by talking about the shape of a distribution. And even the shape has a couple different aspects that we're going to focus on, the first of which is the modality. So we're going to say that a distribution is unimodal, bimodal, or even multimodal, depending on how many peaks the graph of it has. So over here we have two different distributions, and I would say that the main difference between these two is in the number of peaks. So yeah, maybe something weird is going on there, but broad strokes, the first graph has one peak, whereas the second graph has two distinct peaks. So we would say that the first graph is unimodal, whereas the second graph is bimodal. And sure, something could have 3 or more peaks. Once you get past 2, we just call it multimodal. Okay, the other aspect of the shape that we want to focus on is the symmetry. So we might say that a distribution is symmetric, or if it's not symmetric, we're going to say that it's skewed one way or the other. We'll either say that it's skewed left or it's skewed right. So these are examples where we have, let's do that separately. So these are examples of a few graphs that are a mixed bag. So this first one I would say is symmetric because it has an obvious line of symmetry. If you draw a line down the middle, maybe fold it in half, everything would line up evenly. So the first one is symmetric, whereas the other two are skewed. If you drew a line down the middle, the left and right halves certainly look different, and that's true for both of these. Right. So the left one we're going to say is skewed left, whereas the right one is skewed right. And the way that I keep them straight is rather than skewed, I think of it as strewn. So there, for the skewed left one, there are little pieces of this graph that are strewn about to the left, whereas the skewed right one has extra little bits hanging off on the right. Honestly, whatever way makes sense for you to remember which is which, I always mix them up, which is why I have a sort of mnemonic for it. But the point is that this left one is skewed left, whereas the right one is skewed right. Right. The other components of a distribution that we want to be able to talk about is the center and the spread. And we're going to be talking a lot about these concepts in the next couple weeks. But we're going to start off with the most straightforward measures for these things like center and spread. So center is just talking about where the middle is. So if I had this graph, I might be saying, all right, the middle is about here. Likewise, the middle of the second graph, maybe about there. But I want some numerical way of saying, all right, this is the middle of the distribution. So I imagine if I were to ask you, like, what's a way of measuring that? The first thing that comes to most people's mind is the mean. So the mean, also known as the average, we can get by adding up all of the pieces and then dividing by how many there are. So here we have a toy data set. Normally we would want a data set that's much bigger than this, but for these purposes we just have these 5 elements. So the mean we're going to get by adding up 6 plus 7 plus 8 plus 8 plus 12, dividing by 5, and if I did this right, we should get 7.75. So that is the mean or the average of our data set. One reason I went through this is I want to point out one notational way of writing this, and that's summation notation. The general idea is that rather than writing out all of these terms, we can use a capital sigma to represent the sum of those terms. So if these are y terms, then we can say that the sum of all of the y's is this 6 plus 7 plus 8 plus 8 plus 12. So then the sum, or the mean, is going to be the sum of all the y's over n, where in this case, the n is 5. So sum of y's over 5, in this case, equals 7.75. So this is another way of writing down the formula for the mean. Now, the reason we're talking about this is because, well, we all know how to calculate an average. But this form for writing the sigma notation lets us write more complicated formulas in more concise ways. So we're going to see that moving forward with standard deviations and then with a lot of other equations moving forward. The other measure for the middle of a distribution. So we've got the mean. We also have a median, which really just means the middle number. So remember, if our data is still the same as it was before, the median is just saying, all right, whatever number, if you put them all in order, we're going to take the number that's in the middle, and that's the median. So in this case, the median is just equal to 8. Cool. So these are two different measures, two different ways of talking about the middle of a distribution, and they each have pros and cons. The median does a really good job of talking about what a typical entry looks like. So if we had a distribution of all of the ticket prices for Titanic passengers, there's going to be, most of them are going to be clustered around a certain range. This would be an example where we would imagine the prices to be skewed to the right. So the median is just going to say, all right, it's the middle one. It's a great measure for the typical value. In contrast, the mean takes everyone into account. If most people on the Titanic paid £15 to get on board, maybe there were a few super first-class passengers that paid several hundred or thousands of pounds. And while that's drastically different than what the majority are, we may want to take into account these extreme values. So we want to use means and medians in different situations, and we're going to learn as we go on what the appropriate use of each would be. The last attribute of a distribution that we're going to talk about is the spread. So if we had two distributions, and now I'm not going to draw them as histograms, I'm going to draw them smooth, but the same theory holds. If we had two distributions that looked like these, the main difference between them isn't necessarily where their middles are. It's much more about how spread out they are. So if the middle is here and here, well, and they also both look fairly symmetric, they both look unimodal, the difference is that, well, the majority of stuff is in that range for the first graph, whereas for the second graph, maybe the majority is in a narrower range. So this is definitely a hand-wavy type of definition for what a spread is, but the idea is that it's, well, how spread out our whole distribution is. So if we had units on this, say this ran from 0 to 10, this also ran from 0 to 10, maybe the spread here would be about, let's say, 8, whereas the spread here is something more like 4. So now, I just sort of arbitrarily drew these lines. We want a numerical representation that's going to tell us how big this interval is, that talks about where most of this stuff is. And just like with center, there's going to be two different approaches we can take. We can either find the standard deviation, which is analogous to finding the mean, or we can use interquartile range, which is associated to the median. So we're going to talk about each of those.